Okay, so this is again an example of a previous exam problem. Um, so we have a thermodynamic cycle, okay, that goes from 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. We're told that the cycle on the right is made up of the following thermal processes. So 1 to 2 is a process, 2 to 3, 3 to 4, 4 to 1. These are all processes. Um, so I want to point out that if we look at this process, this is actually a very common thermodynamic process. So we did an earlier problem where we had like three processes that we knew and one that we didn't, and we used the three that we knew and a coefficient of performance to find the one that we didn't know. In this case, we know the whole process, right? And we want to figure out the work, the total amount of heat, QH, that flows into the system, and then the efficiency of the cycle, which is the work over QH. Okay, this is just like what they give us what they want for efficiency here, so the measure. Okay, so looking at this, we should realize that we have the Otto cycle here, and I'm just going to kind of show you why that would be the case. I'm hoping that I can pull up the graph. Here we go. So for the Otto cycle, if we look at what's going on here, okay, so we have this 2. They start at 2 here, right? They call it 2a. So basically we would be moving all of our numbers up, right? But there, so we have 1 to 2, right? This 1 to 2 would actually be the last one right here, right? So this one, so for example, so if this was A and this is B and this is D and this is C, we notice that this exact process here, so they're telling us that from these 2 points here, if we go down to the way that they describe the Otto cycle, we can see that this is actually an Otto cycle, right? So from 2 to 3, right? Adiabatic. Um, so adiabatic from A to B, and then B to C, right? B to C, we have this isovolumetric. From this C to D that they have, we have this adiabatic again, and then from D to A, we have this isovolumetric again. Okay, so they're just like moving the numbers around and the way that they're labeling things in the system. So it's going to make our equations a little bit confusing to use this worksheet, but I'd like to try to do it. So just this isovolumetric is listed first. So we should be able to look at this, and because of these labels and the way that the system is set up, we should be able to recognize this one as something called an Otto cycle, which is just like a type of thermodynamic cycle. Oh, wow, spelling. So once we can identify it as this Otto cycle, we should be able to we can apply these general equations for this type of cycle, right? So the way that we can recognize it, we're going to look at our we're looking at our drawing, right? Looking at the graph, the PV diagram, and then we're also looking at the cycles themselves. And because these line up, we know that we have an Otto cycle. Okay, so let's look at some general equations for when we do have an Otto cycle and see what we can use. So this is just kind of a general one for when we do have an overall cycle. So we can say that we have this Q of the cycle, which again is equal to the work, right? As we saw before for the previous video, I encourage you to refer back to that. So in this case, let's go ahead and look at what these would actually be. So this QDA would be Q12. Okay, so what do we know here? So for adiabatic processes, adiabatic, these guys right here. So that's the one this guy is adiabatic. And then this guy is adiabatic. And for adiabatic, we know that Q is equal to 0. So we can go ahead, if you want a little bit more background, feel free to refer back to that. But we're just going to kind of go through the steps of the problem, and we know that we can set these equal to 0, and we can simplify our Q cycle by a lot. Okay, so for our Q cycle, we have Q34, and then we have Q12. Okay, so what are those? So our Q cycle, we're going to go back to our final page on the Otto cycle, and we're just going to take them. Okay. So for this Q34 and Q12 for this cycle, we are going to take this. So we have D over 2 for this, and we're taking BC. d over 2, and then what is our PC? Well, we have, that would be P4, right, for where C is, minus P, and then 3. If you find it easier to follow a template and general equations, if you draw, I would encourage you to have like something like this on a cheat sheet. I think it makes it a little bit easier. And then you can just map out the actual numbers that you would need. Just be very careful. Okay, so this is a general equation that comes from the fact that it is isovolumetric. So we saw this earlier on. So if we're told a process is isovolumetric, we just skipped straight to the fact that it's the Otto cycle, but maybe say like you looked at the problem and you didn't realize that right away. You didn't know that that was the case and that you could do that. If you just went and looked up these general equations for an adiabatic and an isovolumetric process and then used those, you should be able to come to the same conclusions. Okay, so you could use an adiabatic process and then the isovolumetric. So again, for isovolumetric here, yeah. So this is just the delta P. So this delta P is the same, right? So this would be the change in P. So it'd be, P1 to P2. We did it this a little bit of a different way last time, where we just did the difference between these two, right? And then we modeled it as negative if it was going down, so that we had our sign convention modeled correctly. So just to be aware, same approach or same answer, just like a slightly different approach. Okay, so we know for this process that our Qin, just given an Otto cycle, our Qin is going to be equal to QdA. Okay, and this is this guy on this side. So our Qin is equal to QdA here, just given. And then our Q out is equal to QBC. Okay, so in on this side and then out on this side. Okay, so this can maybe help us later. So we know that from A to B we have this is adiabatic, right? And then from C to D, this is adiabatic. So this actually allows us to relate the pressures and volumes between those 2 points. Okay. So what does that mean? So I don't know if I'm mapping this in a way that's like super useful, but I'm just kind of throwing out equations that we're able to use. So because A to B is adiabatic, what that means, so between A and B, let's say A to B, I know that, I'm just going to write the actual numbers here. So I know that P2, V2, right, is to this little gamma, it's going to be equal to P3V3, this little gamma. Okay, so what is this little gamma thing? Like, what the hell is it? What does it mean? Why are we using it? Well, this little gamma value, gamma, is based off of this. So we talked about before, when we either have a diatomic or a monoatomic value, and that we have this d constant, and we set it equal to 5 or equal to 3 in the problems just that we're looking at for this section. And this little gamma value is equal to 1 plus 2 over d. And if I do some interesting math here, I think there's like 1 over 1 minus. That's going to end up just being d over 2. So that's why we see these like equations mapped back and forth. You might see in the solutions, you might see this 1 over 1 minus this gamma in front of an equation like this, where you have like this P3V3. And just notice that they are the same equations, just written in a different form. But yeah, so we have this when we have an adiabatic process, and so we can relate the pressures and the volumes. Okay. Then let's see, when we're going from C to D, this one's also adiabatic from C to D. Okay, and we can say that from C to D, because we know it's adiabatic, we have P4 V3 to this little gamma is equal to P, what was B? Because DIA, BATIC, adiabatic. Okay. Okay. And this this Otto cycle here, I am relating these guys back and forth, right? Okay, so, all right, so how can I use that to solve my problem here? Okay, so I'm given in the beginning of the problem, I know, because I know that this V1 is, I know V1 and V3, and then I know P1 and P2. Well, I also know if I have the volume, so I have a volume, I have V1 and V3, which also means that I know V4 and V2, right? Because if I have this volume, this is going to be equal to, it would be equal to V4, right? V4. So anytime I have these general equations that I need to plug something in, I can say that those are equal. I know that that's true. Okay, what do I do with the pressures? I have this, like, I have P1, so I have pressure at this point, right? P1, and then I also have pressure at this point, P2, right? So what can I do with that? Well, I don't know P4 or P3. I don't know those. So I don't know P4 or P3, but luckily, because I have an adiabatic process, I have these equations here, right? If I can find this, like, P1 and P2 or P2, and I know P2 and V2, I can figure out the pressures, right? Say that P3 is equal to P2 V2 times gamma divided by V3 times this little gamma. And then I can say that P4 is equal to P1 V1 times this little gamma divided by V4 times this little gamma. So we have a lot of similar volumes, right? Unchanging volumes. So these two statements should be equivalent. All right, so to find W cycle, we know that we have Q34 plus Q12. Okay, so for 34, we're going to plug in D over 2 times, and we have this Q12, so plus D over 2. If you are stuck on a problem like this, and you get to a point where, like, you have something that you can't find, please try to set up your general equations as much as you can and just try to get as far as you are able with just solving it symbolically, even if you can't figure out all of the pieces in terms of what you need, right? Okay, so now what can we plug in? Okay, so we know that we have a diatomic gas. So we are setting D is equal to 5 for a diatomic gas. Atomic, diatomic gas. And then the background for why that is true for the diatomic gas. So page 18. So refer to page 18 on these lecture notes here for a little bit more background. Okay, so we got all the equations that we needed from the sheet, and just for the sake of space, so it's a little bit more visible, I'm going to put these away just for right now. Okay, so let's solve for what's going on. Okay, so we were able to use the general equation for work for a cycle. We have two adiabatic heat transfer equations, which means that Q is 0. And then we modeled the rest of what we had for our equations. We had these. And then because these were isovolumetric, we took the general equations for isovolumetric processes. Okay. And then we noted that we didn't have P4 and P3. Okay. So we're like, oh, what do we do with those? We don't really know. Okay, well, can we do anything where we model, 3 to 2 and 1 to 4 using these adiabatic processes? So we did look at 1 to 4, right? 1 to 4, and then we did look at 2 to 3 to figure out that information that we were looking for. Okay. Okay, so let's continue with this problem here. Okay, so we're at the stage where we set up all of our equations, we have everything solved, and now we want to find W cycle. So we have all the pieces that we need, okay? We made the assumptions because we knew what the equations for each of the processes were. We just took them, we simplified from the notes, and we plugged some stuff in. So we're going to say W cycle is equal to 5 halves, and I'm just going to pull this out of the whole thing, P4 minus P over here, okay? And we know that this little, this gamma is equal to 1 plus D over 2. or sorry, 2 over d, 1 plus 2 over d. And then whenever we see this 1 over 1 minus gamma in a problem, the algebra simplifies it down to d over 2. So our equation, even though it looks different from maybe what you see in other solutions, this is still the same, okay? Algebraically, it's still the same. Okay, so don't worry. All right, all right, let's see what we got here. So P4, I'm just going to plug in their numbers just for the sake of time here. Okay, so for the sake of time, I went and I wrote these out for P3 and for P4. So just kind of recapping where we got these from. So P2, we have 2 times 10 to the 5th, and we were given that in the problem, 2 times 10 to the 5th, right, for P2. Okay, so V2, we have 10 to the negative 4 for our V2 here, right, 10 to the negative 4. And we know that because V1 is equal to V2, so we just took the value for V1, right? So our V2 is equal to 10 to the negative 4. V3, V3 is equal to 10, so we're plugging that in. V3 is equal to 10, and then we got this 1.4 for our gamma, and the way we got that is because we know that this gamma is equal to 1 plus, and then 2 over 5 is the same as 4 over 10, so gamma is equal to 1.4, right? 1 plus 4 tenths. Okay, so that's how we end up there. And because these guys are both by gamma, or both to this gamma, we can get them in parentheses and then multiply by the constant. So we're pulling out this P1 and this P2. So just plugging everything in, this is what you get for P3 and P4. And then we're going to be able to just kind of plug that into the rest of the equation for the W cycle part. Okay, so we have all of our values, right? We have this P3 is equal to this, P4 is equal to this. We know what our value is for P2 and P1, and then we know what V3 and V2 is equal to, right? So if we plug everything in, and I'll leave the rest of the math up to you guys, and then I will also, I want to note that this is a previous exam problem, and the solutions are posted. They're also posted on Canvas if you want a little bit more background. But the W cycle in this case is going to be equal to 24.75 joules, okay? So that is our final answer for this problem, okay? And just for reference, I just want to say that, so this P1 and P2 are up there. So just plug in all of your numbers for your W cycle, and this is what you should get, okay? So hopefully that makes sense. So just using the lecture notes as reference, I think that that's a good way to refer back to these equations. And so we just went through part A, and I'm going to stop the recording, and then I'm going to go on to part B next. Okay, so for part B, we're asked to find, this is kind of a keyword, total amount of heat QH that flows into the system. So we're looking for into the system in this case. So this is just some random QH because QH can be like the heat into or out of the system. I think the last time we were looking at a heat sink, basically, so the out of the system for QH. So in this case, we're looking at what's going in here. Okay. So in an Otto cycle, what's going in, we're going to look at this guy, right? We know that for our Otto cycle, Q in is equal to this QdA and we relabeled our points up here, so that's what we're going to go look at. So this QdA. So our Q in is equal to this Q12 value, okay? So Q in for the cycle that they're calling QH is going to be equal to Q1 to 2. Okay, so what is that? Okay, Q1 to 2, or QdA, in this case, is going to be represented by this equation. So Q1 to 2, which we will say dA, right, is going to be equal to d over 2 times P2 minus P1 V2. Okay, so we're just going to solve for this in this case. So far, so good. So I'm just going to go ahead and look. I'm kind of skipping ahead just to make sure that everything's working out okay here. Yep, that looks good. So when we plug in all of our numbers, if you put this into a calculator, I think that whoever this semester, I feel like they must have had a calculator. Well, you could probably this wouldn't be too bad, right? You could 2 times 10 to the fifth minus 1, so it'd be like 1 times 10 to the fifth, and then 50 to over 2. You could do this, it's just, it's a little obnoxious. Just be comfortable with working with your prefixes. Okay, so this could be done without a calculator, just because you're not dividing anything totally impossible. It's just a little annoying. Okay, cool. So that was part B. All right, so then for part C, let's see what else this problem asked us to do here. So for part C, we were asked to find the efficiency of the cycle. Okay, the efficiency of the cycle is going to be the work divided by QH. So we found the work in part A, and then we found the QH in part B. So all we really need to do for part C is just basically divide them, right? So for part C, we're asked to find the efficiency of the cycle, which is W divided by QH. For part 2, we found the W of the cycle. This was for an Otto cycle because we could cancel out these adiabatic processes because we know that Q is 0 for an adiabatic process. We just had the isovolumetric ones left. We used the general equation for heat transfer for an isovolumetric process. And then we used some of the adiabatic equations to relate, or sorry, so A to B is adiabatic and D to C, so this curved line, adiabatic. So we used these equations to relate them, okay? And then these equations just kind of allowed us to find, because we knew that that we could find V1, V2, V3, and V4, but we didn't know P4 and P3, and we needed that. So we were able to figure that out, noting that gamma was equal to this. Okay, so the total answer that we got for the work for the cycle was 24.75 joules, and then the total answer that we got for our Q in, or our heat in, was this. So we're just going to divide them, right? So we're going to have 24.75 joules divided by 25 joules, okay? So basically part A over part B. And then our what we get for this part is 99%, okay? And that is the efficiency.